So the second part would be the lab report. And of course, we focus on the calculations of the worksheet, all right, just to help you a little bit. Now, before anything, what do you need to do for experiment 2 lab report? So where we can find this, it would be in the syllabus. Same thing, like experiment 1, we have 60 points. 32 points of the 60 belong to the abstract writing. We talk about that in a minute. So that's the abstract would be 32 points. The other 28 points belong to the worksheet, WAF, calculation work. So let's talk about this first, the 28 points. So the worksheet, so this is your blank, and you can print and then handwritten, or you can type in and then print. Well, let's take a look at the notes a little bit quickly. So reaction 1, what's the concentration of fructose? Oh, this is task 3 data, right? So where are we? So that will be on page 61, the table. So we have first reaction. Of course, first reaction, you may run many trials, 1, 2, 3, 4, 5, however many trials you have. But anyway, what's the concentration of fructose? What did we say on the table? So 0.20 molar, right, the fructose? So yes, it 0.20? No. How many drops we use? 10. Now student get, oh my God. The big M, this is molar. Molar is mole per liter. Now we're talking drops. What's, I don't know, 10 drops is how many liter? Okay. Trouble. Stuck. Well, what's the lucky? When we combine or add everything together, how many drops? 10, 10, 5. So altogether we have what? 25 drops. So if we've been talking drops, so we cancel out. You see? So 10 over 25, you know, what is 10? 10 drops over 25 drops. So the drops and drops cancel out. So really, we don't need to convert the drops. 1 drop equal to how many liter? We don't really need to do that. But I can tell you, 1 drop is equal to 0.05 milliliter in general. Of course, it depends on what kind of drop you're talking, you know. So everyone, the drop is different. That's why in task 1 we ask you to test yourself to be consistent. As long you are consistent, then you are okay. All right. So what about this one? This one, you will 0.505 times what? Same thing. We get and so on. What about the time? How much time you have? You guys have data? Someone give me data? No? How much time? second. What about reaction 2?
28.
28. Reaction 3?
33.
Anyone else? Anyone different or something? 28. So this a little bit too fast. Of course, now we want to calculate the reaction order, so we compare between reaction 1 and 2. So reaction 1 and 2, the hydroxide is same, and then the fructose double. So the time should be half. So 28 and 10, because it's not quite half. 28 divided by 2 would be 14 seconds, but you have 10. And same thing here, 30 seconds. And compare with reaction 1, I think the fructose would be the same. Hydroxide is double. Again, the time should be half. Half of 30 would be 15, but then you have 10 in your case. So you can calculate the reaction order very similar to experiment 1. So we will compare between reactions 1 and 2, and then 1 and 3. Okay? Now, then you want to calculate the K. The K will be a little challenge this time, all right? So we go back to the lecture notes in here. So the lecture, let's draw a picture. Of our experiment. So this is test tube. A little bit too high. So that never fit in the drawing. So we have oxygen gas. Of course, this would be up in the air, right? So that's roughly 20% belong to oxygen gas. In here, we have the fructose, and then we have the hydroxide. What else we need to have? Oxygen aqueous. This oxygen aqueous is not 20%. My God. So how much oxygen aqueous you can have in this aqueous concentration depends on many things. Of course, depends on what? Temperature? Yes. And then the pressure, of course. Temperature and pressure would be equal. And then what else? The physical. How big is your surface would be also matter. If your surface is very small, it will take some time. I mean, no matter how fast, it will take time to get dissolved. Yeah, or go down. But if your surface is very big, like the beaker, that's why on day 1 I say you use a small size test tube. If you use a big size, then the oxygen will keep coming in. And that's why I say, what happened to our Earth? Our Earth is what? I don't know what happened to our Earth. The Earth's surface is what? We say cut into 3 pieces. 2 pieces belong to what? Ocean, water. Oh my God. We need a big surface of ocean in order to get oxygen go in. Now, how much oxygen is there? It would depend on the temperature. So we have that a little table in the appendix. So when you work on the K, you need to use the table on page 170, all right? Page 177. So we have a solubility of oxygen in water. Assume it's normal pressure. So for example, at 20 degrees C, we have 9.09 milligram per liter. So at 20 degrees C, we have 9.09 milligram per liter oxygen. So different temperature, if you look, so 20 degree and then you look at 15, so 15 would be 10.08. So lower the temperature would be more. Yeah. So different temperature would be different concentration. Now, the other deal is this. So we have fructose. Of course, the reaction is fructose plus oxygen aqueous. But what would be the limiting reagent is the oxygen aqueous. So 1-on-1, 1-to-1, but this is the limiting reagent. So only so much oxygen can dissolve in the water. And once it's used up, then it will use up. It will take time to get dissolved back. It will take time. How you speed up? How do you speed up this go back? Besides the temperature or pressure is what? What did we say? The physical. Array, right? So you increase the surface, or you get the water what? Move. Yes, and that's why I say, oh my God! Every second the ocean is what? Moving, and then they got what? The wave, right? And then also, the fish is very smart. The fish is what? Swim. This part is no more oxygen. They swim to somewhere else. Anyway, okay, let's go back to the calculation here, all right? So, it's not that straightforward. So how much fructose change? Because the oxygen aqueous is the limiting reagent, so we would use that. So even though you have tons and tons of fructose, doesn't matter how much the reaction use up is the oxygen aqueous. So how much is that is equal to the change of fructose? But how do you calculate this one? Is using the appendix 4. All right. So, but in the appendix 4, we provide you is in milligram per liter. But we want to go back to moles per liter. So you need to do a little conversion from milligram to mole. I hope you know how to do that. So then you get the moles per liter, so that's the oxygen change. And divide by the time. The time would be what? For example, we go back to the, so your time is 10 seconds. You see? Then you want to calculate the K. So the K is what you're looking for. So do we know fructose? Yes. Do you know hydroxide? Yes. What's the reaction order? Should be one. Both are one. Both are first order. So you can use one for calculating the K. So how many K we have? K, the rate constant is what? Temperature sensitive, yes? How many K we have? How many temperatures we have? 4, right? Remember last time I said we have 4 different temperatures? So how many K you have? 4. So you are going to do the same thing like last time and make the graph. The lateral log K in the y-axis, 1 over T temperature, in the opposite is the Kelvin. So this one is, so that's the unit in the x-axis. And then you want to find the EA. EA is equal to -1 times slope of this graph, and times R. R is your rate constant. Excuse me, the gas constant, 8.314. And then the A, the Arrhenius constant is E to the y-intercept. Any question?